Dear students, we continue our chapter about derivative. Now the last part. Objectives. Define the differentiability of a function. Recognize the angular point. Study the differentiability of some functions. Materials the same as before. Now, differentiability of a function, page 160. You can read the following definition that simply says, if the derivative exists f prime of x for every value of x exists in the domain, then we say that the function f is differentiable on the domain. Okay, but pay attention. I mean here that the domain of definition of the function derivative should be subset of the domain of definition of the main function f. Example: f of x equal radical x defined on interval I, 0 closed till plus infinity. Is f differentiable on the interval j, 0 open till plus infinity? Simply, we calculate the function derivative applying the rules. We get 1 over 2 radical x. The derivative of radical x is 1 over 2 radical x. This function derivative exists for all value of x except 0 because it is not defined here in the denominator. So we can say that f is differentiable over domain j, 0 open till plus infinity, because the function derivative exists for all values of x in this domain. Okay, and notice that the domain of function f is I, where 0 is closed, okay, till plus infinity. Here we say j subset of I. Back to the definition. You can read it from your book or you can read it here. Okay, we continue. Application. Do it by yourself. Okay. You have f of x equal 1 over x defined over interval I. I ask you if f differentiable over interval I, the same interval. If you calculate the function derivative f prime of x, you will get minus 1 over x squared. Which this function derivative exists for all values of x except 0. So we can say that function f is differentiable over I. So here in this example, we don't have a problem that the domain of definition of the function is the domain of definition of its derivative. Okay, we continue. Now we will talk about another idea, semi-tangents to a curve. Now we are talking about the idea where we have not one tangent to the curve, we have two semi-tangents at the same point to the curve. This point is called angular point. Read pages 159 160 for more information. Definition. If we have point on the curve, at this point for example x equal x0, if it admits two semi-tangents with different directions, one to the right of x0 and the other to the left of x0, then this point is called angular point. And in this case, we say that the function is not differentiable because the number derivative at the right of this point is different from the number derivative at the left of this point. In other words, graphically, the slope of the semi-tangent here is different from the slope of the semi-tangent here, because we said we have two semi-tangents with different directions. Remember that the number derivative represents graphically the slope of the tangent at the point. Example. Look here at this graph. We have piecewise function f of x equal x squared and later f of x equal 1 over x. Is f differentiable at x0 equal 1? Justify your answer. As you notice here graphically, at point x equal 1, to the left of point okay, 1 minus, we have here this semi-tangent, while at the right of point 1 plus, here we have this semi-tangent. So we don't have on point one tangent, we have two semitangents. We say that this curve admits two semitangents at 1. Thus, f is not differentiable at 1. M is called an angular point, meeting point of the two semitangents. Look here. As you notice, graphical interpretation of semitangent to the curve, angular point. What we have here, the first part of the curve, the second part of the curve, at point M, we notice that we have here semitangent to the left of M, semitangent to the right of M. So M is called angular point. Again, simply we say that this function is not differentiable at x equal 1 because the number derivative at left does not equal the number derivative at right, because we have two semitangents, because we have angular point. Application: f of x equal etc. and you have the following curve representing this function. Study differentiability at x equal 1 and interpret your result graphically. Okay, do it by yourself. Okay, first, to study differentiability of the function at x equal 1, we calculate the number derivative at the right of 1. We get the answer. This answer represents graphically the slope of the semitangent at the right of 1. Then we calculate the number derivative of phi prime left at 1, the number derivative at the left of 1, and we get the answer. You can follow the calculation because you know how you do it by yourself. Okay, and this number derivative at the left of 1 represents the slope of the semitangent at the left of 1. Since we have number derivative at the right does not equal number derivative at the left, we say that f is not differentiable at 1. Interpret your result graphically. We say the curve admits two semitangents at 1, forming an angular point. Okay, now we will talk about differentiability of some known functions. We focus on two functions, polynomial functions and rational functions. Polynomial functions, I mean the polynomial form, are defined, continuous, and differentiable over set R. Now, rational functions such as the function 1 over x, rational from ratio, are defined, continuous, and differentiable over their domain of definition. In this case, 1 over x is not defined, neither continuous nor differentiable at x equals 0, because 1 over x different from 0 here. Example: you have this polynomial function. Okay, you remember polynomial functions from grade 10. 3x squared minus 10x plus 5. Is this function differentiable over R? Simply, we say that the function f is a polynomial function applying the above rule, so by definition it is differentiable. Moreover, if we calculate the function derivative, we notice that it exists for any value of x belong to R. Okay, more explanation. As you notice here, this is the graph of a polynomial function. Okay, this is the graph of a polynomial function. What we notice? We notice that for any point on this curve, every point admits one and only one tangent, which means that the function is differentiable at every point on this curve. Okay, so we don't have two semitangents, we have only one tangent at each point. We continue. Application. F of x equal 1 over x. You should check whether this function is differentiable over set R. F defined here. I'm asking about differentiability over set R. Do it by yourself. Okay. F of x equal 1 over x is a rational function defined over its domain. Now we can say this function f is differentiable, but it is differentiable over its domain. So this function is not differentiable over set R because simply it is not defined at x equals 0. Remember, I ask you if it is differentiable over R while it is only defined on R star. X does not equal 0. So simply, since the function is not defined at x equals 0, we say the function is not differentiable over set R. If you try to calculate the function derivative, we get minus 1 over x squared, which assures the idea we said it exists for all values except 0. Assignment. Homework, you have exercise 18 part C, and this is the question. Okay, if you don't have your book. And I gave you the following hint. Okay, pay attention to the hint. Thank you for your time.